So throughout the year, we've kind of been referring to kinetics indirectly. So we're going to kind of take the time now to officially talk about it. What kinetics is the study of reaction rates. So reactions occur because molecules and atoms are colliding with each other. So this happens regardless of phase. If you have a solid or you have a liquid or a gas, they're still doing this. It's just they're doing it in different ratios usually. So the more often molecules and atoms collide, the faster the reaction goes. This makes sense to us. The more things you have in your substance, so whether it's a solid, liquid, a gas, or aqueous solution, the more particles that are there, the more likely they are to react. All reactions require energy for them to occur. So we have this thing called E of A, which we refer to as the activation energy. This is the energy required to start a reaction. You can kind of think of it as a barrier. So the best way to look at this is by looking at an energy diagram as listed here. So this is an endothermic reaction. An endothermic, you end up with a positive E, which would be a positive energy, indicating that energy is absorbed. An endothermic reaction, energy is always absorbed. You can kind of think of it as En, like entering. Energy is entering the reaction. So looking at this reaction diagram or energy diagram, you can see the reactants have a lower energy than the products. Since the products have a higher energy, we know that energy is going to be positive here because of that. So you'll notice too we have this E of A. E of A is the energy required to start the reaction. You can kind of think of this as going on a bicycle up a hill. So if you don't get to the peak of the hill, you're not going to be able to make it over. So if you're on your bicycle and you're working your way up the hill and you stop midway because that's all the energy you have, you're just going to kind of roll back down the hill. You're not going to be able to go through the reaction process. Every reaction has its own unique activation energy. Some reactions are going to require a significantly larger activation energy. Others are going to require a smaller one. So if we go back to look at an exothermic reaction, then exo, you can kind of think of exit, meaning energy is leaving the reaction. So a negative energy is indicating that energy is released. So it's set up very similarly to an endothermic reaction, except now our reactants have a higher energy than our products. So again, you can kind of think of the analogy of riding the bike up the hill. So if you were riding your bike up this hill, you get to the peak. This would be a really nice hill to go down because you would get more energy out than you put in. So you could go down the hill very quickly. So your delta H here is negative, indicating that the energy is being released. So how do we go about starting a chemical reaction? So if the molecules or atoms collide with less energy than the activation energy, they just will bounce apart unchanged. You have to meet that minimum energy threshold for the reaction to take place. So there's a few things we can do to increase the rate of the reaction. The first thing is we can increase the temperature. So as we already know, there's a direct relationship between kinetic energy and temperature. The higher the temperature, the faster the molecules will go. More chaotic motion will lead to more collisions. So that's the first thing that we can do. The second thing, we can increase the surface area of our reactants. The more sites we have exposed to react, the more collisions can occur. So if you have a piece of copper versus many small pieces, that large piece, the reaction or the chemical can only react with the outside. The smaller pieces have more surface area, allowing for more reaction. And then the last thing we can do is increase the concentration. So the more moles, meaning the more particles available to react, we have a faster reaction take place. So if we had a 6 molar solution versus a 0.1 molar solution of an acid, the 6 molar solution is going to react much more quickly. This is why when we do labs involving acids, we use the lower concentrations, because we want to make sure that if it reacts with your skin, it's going to react slowly so you can wash it off in time. So another thing we can do, we can add a catalyst. So this is going to speed up the reaction by lowering the activation energy. So if a collision takes place of two different particles, we're then able to more likely, with the catalyst present, we're able to more likely to have the reaction occur because we're lowering the hill, or we're lowering the activation energy required. So the activation energy with the catalyst is significantly lower than with no catalyst. So a catalyst is part of the reaction. However, it's not something that's incorporated in the reaction because it's not used up. It can be used over and over again. It's kind of like an enzyme in biology. The enzyme, until you have an inhibitor in it, it's going to continue to work for your process. So we have a few questions to kind of answer here. So why do reactions occur at different rates? Well, it has to do with the chemical nature of the substances. All chemical substances have slightly different properties, and when you combine them in a chemical reaction, it's going to affect the rate of the reaction. So what prevents a reaction from occurring immediately? Well, it depends on the speed of your particles, it depends on the concentration, and it depends on the chemical nature of your particles. Some reactions require a very high activation energy, so it's going to take a significantly longer time for that reaction to start than if we had a lower activation energy. Why don't all products form at the same instant? Well, we can't have everything react perfectly from the get-go. Most chemical reactions that we have done in this class have been quick reactions that we can't really see the reaction occurring, that it's kind of just done. But there are chemical reactions that are much slower, so it takes longer for the product to form. So there's so many conditions for each reaction. It often takes longer for some to arrange themselves so that they can react to form new substances, is what the bottom part's saying. Chemical equilibrium. Chemical equilibrium is a state when the concentration of all substances in a reaction remains constant. So up to this point, we've kind of assumed that a reaction goes one way. We have reactants, we make products, and then we're done. However, most reactions actually go in both directions. They go in the forward direction and the reverse reaction, or reverse direction. So in other words, up to this point, we've assumed all reactions go to completion, meaning they just kind of stop. However, most reactions are reversible. So from this point forward, we're going to be drawing kind of these double arrows to indicate that it's a reversible reaction. So there's a couple different ways you could draw these reactions, or the arrows. You can draw it like this, or more often you'll kind of see this kind of half arrow in each direction. That's kind of more common. It's just with formatting in Microsoft Word, it can be a little bit difficult to get the correct symbol in. So the reverse arrow indicates the reaction can occur in either direction until equilibrium occurs. So equilibrium is when you have constant concentrations. So you won't be able to detect a change. However, you're still having the forward reaction occur and the reverse reaction occur. So equilibrium is when no net changes occur. But on the molecular level, the reaction is still occurring. So there's no changes in concentration once equilibrium has been established. So looking at this graph, this is a good way to help us illustrate. So when we start a reaction, we only have reactants, which in this graph is visualized in red. We only have reactants, we have no products. So right away, we're going to very quickly decrease our concentration of reactants and increase our concentration of products. There's going to be a time, though, where you're going to have a constant concentration of products and a constant concentration of reactants. This is where equilibrium is established. The reaction is still ongoing. The reaction has not stopped. Equilibrium reactions will never stop. It's just you're not going to be able to detect a difference. So these statements are referring to the reaction above. I rewrote it here so we could talk about it. So we have water and carbon monoxide. They're going to decrease over time because they're reactants. So they're going to go away. Hydrogen and carbon dioxide, the products, there's no concentration initially, but but over time they're going to be formed. So we're always going to have the forward reaction, and we're always going to have the reverse reaction. When their rates are equal to each other, that's when we're at equilibrium. Now, I want you to think about this for a moment. Just because it says equilibrium, it's because the equal is in it because the rates are equal. It does not mean you have an equal amount of reactants and an equal amount of products. Every reaction is going to be a little bit different. You're going to have a different ratio of reactants to products. Usually you'll have more products than reactants. However, it can be any ratio in between. With kinetics, we saw that the rate of the forward reaction slows because the reactants are being used up. The opposite applies for the reverse reaction. As you're using up particles, it's less likely you're going to have two of the particles you need to collide. Once some of the products form, they can start reacting together to form the reactants again. The rate of the reverse reaction starts slow, but it increases. Again, when the rates of the reactions are equal, equilibrium has been achieved. So it doesn't necessarily mean equal amounts of reactants and products. So this brings up the idea of an equilibrium constant, which we refer to as K or Kc. So we have a lot of constants up to this point. This is the specific constant for equilibrium. It was derived from experimentation. So what we're able to do with this is we're going to be able to determine what the reaction is. Does it favor the reactants, so more reactants are going to be in the reaction, or more products at equilibrium? So I kind of made up this reaction where our uppercase letters represent our chemical substances and our lowercase letters represent the coefficients out in front to balance it. So K is going to be equal to the bracket. The bracket indicates concentration. These are square brackets, not the fancy brackets. So we have products, the concentration of our products to the exponent of each multiplied together, divided by the concentration of reactants on the bottom, again, to those coefficients. So this is referred to as an equilibrium expression. The nice thing about this is you're actually able to calculate concentrations of all of these things. We don't really have time to spend calculating the concentrations of these things, but that would be the next logical step. If you go on to take AP chemistry, that'll be one of the topics discussed. The most important part of our equilibrium constant equation is that we only include aqueous and gaseous substances. These are the substances that can go into the expression because they're the most accessible for equilibrium. So concentration of only those two things is going to change significantly. When you have a solid or a liquid, you usually have such a large amount that it won't significantly affect the reaction. So pure solids and pure liquids, we don't use in our equilibrium expressions. So there are actually two different types of equilibrium. We have homogeneous equilibria, where we have substances all in the same state. So if we had a reaction that everything was a gas, it would be considered homogeneous equilibria. If we had gases and liquids, or gases and something else, or anything else really, it would be heterogeneous because you have the mixture. Both types of reactions can occur. Okay, so one of the things that we talk about here is the magnitude of K. So remember, our K is reactants on the bottom, the concentration of reactants, and the concentration of products on the top. So a larger K value is going to indicate the reaction is going to go towards completion. So in other words, it favors the products. So if you're thinking of this from a numerical standpoint, you have more products than you do reactants when you have a large K. A small K means the reactants are favored, so not many products are going to form. So we're going to write our K equation for this reaction. So they gave us the reaction in word form, so we'll have to first write out the chemical equation. Sulfur dioxide, which is SO2, reacts with oxygen gas to form sulfur trioxide. Now, it didn't specifically say gases for all of them, but at the end it told us they were all gases. So they'll all be included in our K equations. So we wrote out our reaction. We now have to balance it. If you don't balance it, you can't write out the K equation. So we balanced it, we needed two 2's. Since all the substances are gases, they will all be included in our K equation. So products are going to go on the top. We use our square brackets, so we have SO3, and then we're going to have the exponent of 2, so we're like squaring it. And on the bottom, we're going to have O2 in our square brackets and SO2. And SO2 will also be squared. So this allows us to calculate K based on the concentration values of those substances. So I want you to write out the reactions for these last two, and then we'll take a look at our Ks. So we wrote out the first one. It is balanced, so there's going to be no exponents there. In the second one, it is a heterogeneous equilibrium. We have gases, we have liquids, we have aqueous substances. It doesn't explicitly say that the water is a liquid, but because we're dealing with water, it's a liquid. It's a pure liquid for us. So because we have the liquid, we're only going to include things that are either gas or aqueous. We are not going to include water in our equation. It is balanced, so we don't have to change, we don't have to write any coefficients. So our K is just going to be H2SO4 on the top and then SO3 on the bottom. So if we were to calculate this, we would take the concentration of sulfuric acid divided by the concentration of our sulfur trioxide.